just to establish the problem we're trying to solve. So as you heard earlier from Nathan's talk, in our codec we use lap transforms. Other codecs also use things like wavelets and stuff. And that, a transform stage is designed to remove blocking artifacts or eliminate blocking artifacts. So if you then do motion compensation in the normal way, which is block-based, then you'll add blocking artifacts that are now expensive for you to correct in the transform stage. So we want to avoid that. There have long been solutions proposed for this. OBMC was proposed in the early 90s. Basically, you do block-based motion compensation, but you overlap the blocks and blend the things together using the blending window. But that all worked great for fixed block sizes. But these days, people use highly variable block sizes. So you may have blocks ranging from 64 by 64 all the way down to 4 by 4. And you get a lot of gains from being able to, in the non-overlap case, you get a lot of gains from being able to use these variable block sizes. But it is not obvious how you would do that with OBMC, because now you have a very complicated blending window that you construct. So, sort of the usual approach for this is to just do all of your overlaps with the smallest block size. So this would be equivalent to, if I had a 64 by 64 block, just pretending it's a bunch of little 4 by 4 blocks and only doing the 4 by 4 overlap with my neighbors, right? And so this was done by Dirac. I think Qualcomm had a recent proposal to study group 16 that suggests doing the same thing for an HEVC extension. And this is, this works, but it's not really variable size, right? It's basically just a better entropy coding method for having fixed size blocks. Because what you're really doing is just saying I have all these little tiny blocks, and then I'm coding that they all have the same motion vector efficiently. So there was actually a paper in the late 90s by Zhang et al. that proposed doing something called adaptive repartitioning. And the idea is that it would split the large blocks until the overlap was, quote-unquote, compatible with their neighbors. The idea that the amount of overlap you had to do with your neighbors was less than 50% of the size of the neighboring block. And so that would let you use larger windows in at least some areas, depending on how your neighbor was constructed. So that if you had all large blocks, then you would use all large windows, and if you had some small blocks, well then some of your large block would be overlapped in large size, and maybe some other part of it would be overlapped with a small size. But that still means that if you have large blocks, some of them might only use a small overlap, and it also didn't tell you how do you actually do your search in the encoder to decide what block sizes to use, right? So this was done in the late 90s. The idea of doing some kind of exhaustive search over all combinations was basically ludicrous. And what they actually did in the paper was they just did normal block-based motion compensation to do the search, and then they said now we're going to overlap it. They didn't actually consider the overlap at all when they were doing the encoder search. But still, the results were encouraging, right? So this is a graph from that paper. The line there at the top is the no overlap case, and the one sort of in between there is the fixed overlap case, which is what people have usually done. This idea of doing adaptive overlap, where you could at least use the larging blending window. In some cases, it looked like it performed much better. So what we propose to do is basically a slightly cleaned up version of that proposal back then. So the idea is that I'm going to restrict the adjacent block sizes to differ by no more than a factor of 2. Right? So I can have a 64 by 64 next to a 32 by 32, or I can have a 32 by 32 next to a 16 by 16, but I can't have a 64 by 64 next to a 16 by 16. Right? And we're going to borrow this data structure from the computer graphics community called a 4-8 mesh to impose that restriction. So this is used for surface simplification in computer graphics. And the reason I'm doing that is because this actually has a good search algorithm. So I can actually do a reasonable search considering the overlap in my encoder. And then given that restriction that these block sizes differ by no more than a factor of 2, then I can define interpolation rules based on that. So what is a 4-8 mesh? Basically, the idea is you start with the mesh at the largest block size, and here all of the little circles are where we're coding motion vectors, and then we do interpolation inside each one of these blocks from 4 different motion vectors. So at the odd levels of this 4-8 mesh, you can add a new motion vector to block centers, right? So I'm only adding one motion vector, but now I have 4 new blocks at a smaller block size. And the idea is that we can only add that motion vector if we have 2 parents that exist in the mesh already. And so in that level 1, we always have all the level 0 motion vectors, so we'll always have those 2 parents. So I can add several level 1 vertices. Now we go to an even level. So at the even level, I add new motion vectors to block edges, right? And so again, I can only do that if I have 2 parents in the grid. So I can add that motion vector that I've shown there because I have the 2 adjacent neighbors, but I couldn't add ones to the other block edges in this because I don't have the corresponding level 1 vertex. But you could, suppose adding all of those, and you get the next odd level, you add more to the block centers and then more to the block edges as you go down, right? So given that, you can then define relatively simple interpolation windows. And so I'm not going to give the details of the math, that's in the paper, but basically these are all just simple sums of bilinear weights, right? And so this is showing 2 examples of that. Having say a 16 by 16 next to some 8 by 8s, you can see that the blending window inside of the 16 by 16 half of that does not change regardless of what happens in the block next to it that's split into 8 by 8s. So they're just constructed to match along that edge. And because they're simple sums of bilinear weights, they're very cheap to compute. Like, we don't have to have tables for all the different cases. We can actually compute all the weights on the fly with 1 add per pixel. And so all that works out very nicely. And now we can talk a little bit about how we actually do the search in the encoder, right? And so the observation which was made by Balamelli in her 2001 PhD thesis on surface simplification was that sort of greedily inserting and removing leaves in this tree does poorly. So the rate distortion objective is not monotonic, and you might have to add several different motion vectors that regress rate distortion performance before you can add one motion vector that improves things a lot. And so the approach that she suggested was using general decimation. And the idea is that you start with a completely full mesh, and you remove vertices one at a time, but instead of just removing the leaves, you try to remove every vertex, and if it has some children in the mesh, then you remove all of them too. And so the idea is that I might remove one vertex that gets rid of all of those vertices in my mesh, and you compute the change in rate distortion performance for removing all of those at the same time. And so if you actually look at doing this for a number of different lambda values, if you do sort of the greedy approach, you get this thing at the bottom where the result is actually not even monotonic, right? Like, I might actually try to say I'm going to spend more bits removing distortion, and distortion goes up instead of down. But the general decimation is not perfectly monotonic, but you can see it does much better. So the actual completely global optimal solution is MB hard, but at least this general decimation technique gets you much closer to something that is reasonable. So we implemented this in our codec. This result was not published in the paper because this was really just a quick 2-hour hack experiment. So we had never actually compared our variable block size overlap motion compensation stuff to just normal variable block size motion compensation, but I did do an experiment, and you can see we actually get a significant gain from using the overlap block motion compensation. So the difference there is about 1 dB, which is what you normally expect for overlap block motion compensation versus fixed size overlap block, fixed size non-overlap block motion compensation. So we still retain all the same gains that you get for when we start using variable size blocks. Blocks don't differ by more than a factor of 2, but all you have to do is keep the edges between the different sizes unsplit, so you can't add any extra motion vectors to those edges. And however, the result is no longer a 4-8 mesh, and your search becomes a little bit more complicated. We haven't worked out the details of all of that yet, but it's certainly possible to do. Currently, we only support just 16 by 16 block sizes, so that's obviously something we want to improve in the future. And there's always ways to do better motion vector prediction and better encoder searching and all that sort of stuff compared to our current implementation. So to sort of give you some of the idea of the overall performance, so currently Daala does significantly worse than 264 and 265 in terms of PSNR, but if you saw the PBQ talk earlier, that's not that surprising because we do a bunch of things that actively harm PSNR, like activity masking. If you look at some of the more perceptually oriented metrics like PSNR HBS, we start looking a lot better. This one generally tends to tell you, at least in our experience, like how well you do on clean edges. So fast multi-scale SSIM, we look even better, and that generally tells you how well we do on preserving texture. And so if you saw the PBQ talk, that should come no surprise that we do very well on that one. So I think this probably overstates the case, and this one probably understates the case, and our real performance is somewhere in between those two, but it shows that you can actually build a codec that's at least competitive with the state-of-the-art things using lap transforms and overlap block motion compensation. So resources are the same as before. Do we have any questions?